let's try solving some systems of equations that aren't linear systems of equations. So we'll use the same general idea as for linear equations, but what we'll see is that the possibilities for the number of solutions you can get is totally different with nonlinear equations. So remember, with a system of linear equations, you either get no solutions, infinitely many solutions, or exactly one solution. What we'll see with nonlinear equations is that you might get any number of solutions. So just to take an example, let's solve this system of equations. Now, we can use either the substitution idea or the elimination idea. I would say, in general, with nonlinear equations, the substitution idea is a little more consistently useful. So to use the substitution idea, why don't we take one of these two equations and solve it for one of the two variables? You want to use a little judgment in choosing which equation and which variable. I think if we solve this second equation, we can solve it for x or for y, but if we solve it for y, then we're going to have to plug some messy thing into this y squared thing, and we're going to have to square it. So let's save ourselves the work and solve this second equation for x instead. So when we do that, we get x equals y plus 2, and now we can plug that into the first equation. We get y plus 2 minus y squared equals negative 4. And now we have an equation that only has y's. There aren't any x's here, so we can solve this for y. Let's see. What should we do? Let me just rewrite the left-hand side. So y squared plus y plus 2 equals negative 4. Let's get this negative 4 to the left-hand side. So minus y squared plus y plus 6 equals 0. And then let's multiply everything by minus 1, just because I like having my y squared term be positive. So y squared minus y minus 6. And now I see that this factors. So this is y minus 3 times y plus 2. Okay, so this tells us that y is either 3 or the other possibility is that y is minus 2. Now remember, to solve a system, we need to find a value for every variable. So here we have two possibilities for y. That means for each of these possible y's, there's an x that goes along with it. And to find the corresponding x's, we can just take this equation, or maybe this one right here, right, and plug in the y values to see what the corresponding x is. So when y is 3, we get x is 3 plus 2, so that's 5. So one solution is 5, 3. And when y is minus 2, so now we get x is y, which is minus 2, plus 2, so that's 0. Okay, so this gives us a solution 0, comma, minus 2. Now geometrically, what's going on here, the reason why it's possible to have two solutions is because right, a nonlinear equation can give you a curve in the xy plane that is much more complicated than a linear equation. A linear equation can only give you a line, but this particular nonlinear equation happens to be quadratic. So it's going to give us a parabola. So it's what, x equals y squared minus 4. So that's going to look like this. And then this line, x equals y plus 2, is, let's see, that's the same thing as y equals x minus 2. So it is going to be something like this. Okay, and you can see we have a line cutting across a parabola, and so we happen to get two intersection points for this particular one. And there's 0, comma, minus 2 down here, and then over here that's 5, comma, 3. You can see if we had more complicated curves, we might get any number of intersection points for two curves. So if we had a nonlinear equation that gave us this curve, and then a nonlinear equation that gave us this curve, we'd have lots and lots of intersection points, right? 1, 2, 3, 4, 5, 6, 7, 8 of them for this example. You can see we could get any finite number of intersection points, or I mean, we could also get infinitely many intersection points as well, as with as is possible with linear equations. So one thing that's more complicated about systems of nonlinear equations is you might get any number of intersection points. And another thing that's more complicated about nonlinear equations is there's no set fixed procedure to solve the system as there is with linear equations, right? With linear equations, all we had to do was set up the system correctly and then sort of use certain terms to zero out other terms, and then you get a solution. But it's not that simple with nonlinear equations, just because nonlinear equations can be much more complicated.